Do we start?
Yes.
Okay. So hello. I wanted to talk about polylogarithmic cuts of models of weak arithmetic, where I think it's a good view of simulation properties between different propositional proof systems in a more model theoretic way. So I guess it's not. I guess the theories I use are not so well known, so I will give a brief introduction and some motivation of why it looks like it's a good idea to look at models instead of the syntactical versions. So I will work in a two-sorted setting. So I have a universe U1, which basically are the numbers, and I have universe U2, which are bounded sets. And now we want to do some arithmetic. So what we need is a language that gives us, we need addition, multiplication, some ordering on the numbers, some size measure of sets, and then we want elementhood and equality for numbers and equality for sets. So one thing I want to say about the size is not the classical size, which is the number of elements, but we think of the size of the length of a characteristic function which gives us the set. So this is basically the largest number in a set plus 1, because we also want to have the empty set as something. So now this is this can basically, if you don't like it, you can think of it as something like PA minus, and now we have to add some induction and some comprehension. So we have a weak induction and we have some weak comprehension, like an axiom that tells us which sets actually exist in our models. And so the model I'm interested in at the moment is called V0. And it basically is all of this. So we have some, well, so PA minus is like the properties we have on these connectives, and then we add some weak induction and weak comprehension. And in V0 we basically have sigma V0 induction and also sigma E0 comprehension.
B stands for bounded?
Excuse me?
The B stands for bounded?
Yep. So basically it's these are formulas that only contain number quantifiers. They don't contain any quantifiers of the second sort. So and now I want to have a look at the models and then to get some some intuition on why it's interesting to have a look at the polylogarithmic cuts, which are pretty small parts of the models. So if we have some model of, let's say, size n of V0, then these are the numbers, and we have some sets in the model. Looks like this. So if I have the logarithmic part of these models, I can see that all the sets here correspond, like a set in the logarithmic part, a small set. It basically corresponds to a number. Okay. So if I so I have a much stronger induction on sets on the small part than I have on the large part. So the set can look much more complicated than the set on the full model. And the intuition is that if I go a bit higher, and I take a polynomial of log of n, then I also should have still a bit stranger models. Maybe not as complicated as this one, sets, I mean, not as complicated as this one, but also rather complicated. So maybe like, I don't know. So so the question is, if I have a big O, so a natural question I think is that if I have a model of V0, and this is the polylogarithmic part of it, what does it model? The question, if n is the model of V0 and m is the polylogarithmic part or cut, then well, M models would. So to kind of talk about this question, it's a good idea to maybe define polylogarithmic cut before, which I actually just forgot. So if I have some model n, let's say of V0, then a cut, then we call a subset M of n a cut if, first of all, the numbers in n should be a subset of the numbers in n, and then we would like to have that the constants are the same. So 0, so I forgot, we actually also have constants 0 and 1, and they should be the same. So the 0 in m should be the 0 in n, and the 0 in the 1. The 1 in m should be the 1 in n. Then we want to be closed under addition and multiplication. So m1 is closed under addition, multiplication, and downwards closed under the ordering. And then the sets should be the ones that are bounded in n. So n2 equals all the sets in n2, such that the size of x is in m1. And then the other relation symbols, the other symbols are simply the restrictions. Functions and relations are restrictions from n. Okay. So that's a general definition of a cut, and I think, and I want to call such a cut, polylogarithmic if we can say that x is in m1 if and only if there exists an a in n1 and there exists a natural, like a standard number k, such that x is at most the length of a to k. So that's basically exactly what we have here, the situation. So now,
I think you mean there is an a in n1 such that x is in m1 if and only if.
No. It has to be standard. Okay. Sorry, what?
Well, look, everything in n1, for everything in n1, you can find such an a.
Well, but it's the length of a, right? I mean, that's the log.
It's
That's the log.
I'm sorry.
Okay. I mean, it's still good because I actually didn't define the log in the sense, but.
Well, and you're not assuming that the model you start with is closed under exponentiation.
Huh? No.
You're not assuming that.
No. That would be too much. So now, if we have this setup and we ask us this question, then we can show that if n is a model of V0 and m subset of n is a polylogarithmic cut, then m actually is a model of V and C1. So this is another arithmetic class that comes from a complexity class. It's actually corresponding to NC1 computations, and it is basically V0, like this, the class we have up here, added to the, if we add some predicate that gives us the value of monotone functions. So we can evaluate any monotone function in this class. In this class, it's probably not possible in V0, but in VNC1 that's possible, and it's the action. So maybe I just write it down. VNC1 is V0 plus monotone formula value, by which I mean we get an evaluation. For any formula, we get some predicate that evaluates us, that gives us the value of the formula, and that is actually, and I mean, it's not only giving us the value, but we can compute it from the formula, given as a tree. So, so I thought I give some idea of the proof. It's actually not too complicated, the idea, and yeah, and then we'll see. So, so the idea is like we want to formalize a version of Nepomniachtchi's theorem. That's a theorem that is that says if something is computable in a very weak Turing machine, we can actually define it in delta zero in the standard setting. So here we will get a sigma B0 definition, and then using comprehension, we will get that it is actually a part of our model. So what we do first is prove a version of Nepomniachtchi's theorem that is like if Y is some kind of language in the computer science theoretical sense, is computed in time space n to the c n to the epsilon for some c, well, at least 1 and epsilon smaller than 1. Then, well, so I write it a bit briefly. So the for any k, the restriction of y to this interval, to the interval 0 to m to the k, is in n2. For m in m1 and k some standard number. So if we can, so we have a proof. If we have a proof of this, then it is sufficient to give an algorithm that can evaluate the formulas in a standard sense. So if we have a formula, we can just think of it as a tree. That's some formula phi. It's a monotone formula, so we only have connectives and or in here, and it's binary like this. And down here are the variables. And if I want to evaluate it, I don't have to use much memory to do it. I only have to have one path, and I can evaluate it in a bottom-up fashion. Like it's a very standard way of evaluating formulas. So we get a well, Poly, time, and log space algorithm for evaluating any formula. And so by this version of this Nepomniachtchi theorem, the evaluation, which is a string of the values of the tree, will be a set in M2, and therefore M will be a model of VNC1. So so why is it interesting to do this? I mean, apart from it being interesting from this model theoretic perspective, maybe it's also interesting because there's a relation between complexity classes, between propositional proof systems, and these theories. So we know that if phi is a sigma B0 formula, and no. Then provability in a weak arithmetic theory corresponds to efficient probability of the translation of this formula in a propositional proof system. So for example, if in V0 we can prove for all x and for all x, phi x and x, then this corresponds to efficient probability in Frege, which is a Hilbert-style calculus, if you don't know it. So we have efficient probability in a Frege system of the translation of phi, which I denote like this. That's a family of propositional formulas, and this is a two-sorted, like sort of second order formula. And this is not true because this is bounded depth Frege, which is like a Frege system, but the formulas we can use in our derivation are all bounded by some global constant. So, and if I have VNC1 prove such a thing, then I have a correspondence to normal Frege proofs. So what does it have to do with these models? I can perceive a proof as a set in such a model. So let's say we start. Well, so let's say we start with the model of VNC1, and we are able, or we start with an efficient proof of some formula in Frege, and then we can assume that we have some derivation of some corresponding formula in VNC1. So this gives us, if we have an arithmetic model of some size m, then we get like this could be this the set, and this could be a proof of phi. So now, because of this result, I know if I extend this model to something like 2 to the m by 1 by k, it depends a bit on the size of this proof, how much I have to extend it. Then this part is a model of VNC1, but the whole part is a model of V0. So now I can perceive this proof either as a large proof in this model, or I perceive it as a very small proof in this model. But nonetheless, I have proved the same. And now because this corresponds to bounded depth Frege proof systems, and V0 corresponds to bounded depth Frege proof systems. As a corollary, we get a recent result by Filmus, Pitassi, and Santana. That says that bounded depth Frege sub-exponentially simulates Frege. So if I have a general proof in Frege, I always get a short proof in Frege. I will get a not extremely bad proof in bounded depth Frege, not as bad as possible, certainly. So I think that's 2011. That's last year, I think. So yeah. Oh, it's a bit short. So I also want to give an outlook why this is also interesting from some automatizability point of view. So if you have such a result, there's a lot of open questions you can address. So what happens if you change the underlying theory, like this V0? You can make it stronger and you can make it weaker. And I think especially the case when it becomes very weak might be interesting, because if so, we have this V0, and we can strengthen it, or we can weaken it. And what happens to the theory in the cut? What happens here? We know we have VNC1, but when we strengthen it, what happens when we weaken it? Also, what happens? So a rather natural, well, not natural, but if we weaken it very very long to a theory, it's called T21. Then we have a correspondence to to a proof system that's called ResLog. And ResLog is interesting, especially because there's a correspondence between automatizability and resolution, which is basically the standard proof system for anyone who tries to automatize anything in these proof systems, and interpolation property for ResLog. So so there's a result by Acerias and Bonnet, I think 2003, that says if ResLog doesn't have feasible interpolation, then resolution is not automatizable. So if we could prove that we don't get some sort of feasible interpolation here, then we know that resolution as a proof system is not automatizable. This is interesting because if we have a look at this cut, we know it is stronger, and if you have a look at the bounds, I didn't say much about the bounds, but if you have a look at the bounds here, you can calculate that actually it would be okay to prove here that you can that you have efficient proofs of some cryptographic conjectures. For example, if you could prove in this cut that something called Diffie-Hellman, which is a public key cryptographic key, it's a key exchange scheme. If you could prove that this is correct, by which I mean that no code word can be translated by the algorithm to 0 or to 1, then this would give us then if ResLog had feasible interpolation, then this would give us an attack against Diffie-Hellman. So if we assume Diffie-Hellman is secure against 2 to the O of m to 1 by k attackers, then we would get that resolution is not automatizable by this argument. But the point is, I didn't have time to get into the argument how you actually prove that this is a VNC1 model, but the amount of quantifiers you have in this theory is so small that it certainly doesn't look like you can do it like this. You have to have a more involved argument to do this. But I think it's still a nice connection between probability in these systems and some automatizability results for like resolution and such. And I think I'm done.
Thank you. And for questions?
Can you just say again what was the power of the log n?
Of log n?
Yeah.
Well, if you have log n, then every set corresponds to a number. So you basically have full induction in this kind of submodel. So
it's all bounded arithmetic hierarchy.
yeah, basically, yeah. So that's very strong. That's also the reason, by the way, that so here T21 is not such a standard model because we don't have the smash function in this theory. But if you add the smash function, then polylog cuts and log cuts would coincide. So this would be a very tight result. You can't have, the numbers would work, but it wouldn't work if you go too far away from the proper result. So if I go for t to 2 here, then this doesn't work anymore. And also, if I'm not wrong, log n and polylog n cuts would coincide. So, yeah.
More questions? Let's thank the speaker again.